All right, so this is going to be the last section in chapter 9. So we're going to talk about planetary motion and the orbits. So some of this you know already, but we're also going to look at some of the reasons why things go in the way that we know that they've gone for so many years. All right, so Newton showed that the same law of gravity that operates on the surface of the Earth applies to the moon and other objects as well. So Newton's universal law of gravitation that we use for Earth also applies to every other astronomical object. So let's move this up here. There we go. All right. So Newton reasoned that if you were to launch an object from the top of a mountain or anywhere, and it had enough speed, in the absence of air resistance, that object would go into orbit. And you can see the diagram that he drew here. So here's your mountaintop. If you launched it with enough speed, instead of just going off, it would begin to orbit the Earth. Okay. All right. And so a description of the planetary motion, though, why they move in the way they move, has always been a problem. Why do they orbit in the path that they do? And it wasn't until Johannes Kepler came up with his 3 laws of planetary motion that those problems were kind of solved. And then Newton later showed that all 3 of Kepler's laws were a consequence of his law of universal gravitation. Okay, so they kind of go hand in hand. All right, so we're going to look at Kepler's laws first. And Kepler's laws just kind of describe the motion of a planet and describe their orbit, whereas Newton's universal law of gravitation explains why it has that particular motion or orbit. So Kepler's first law states that planets follow an elliptical orbit with the sun as one of the focal points. And you can see the image here, the illustration here below. So here's your focal point, one of the center points. An ellipse has 2 center points, not just one. So the sun makes up one of those focal points, and then the planet orbits around that sun in that particular path. So that's Kepler's first law. Planets follow an elliptical orbit with the sun as one of the focal points. Newton was able to show mathematically that because the force of gravity decreases with the inverse square of the distance, then closed orbits have to form ellipses, okay, or circles, one of the two. So Kepler's law describes the motion. Newton's law explains why it has to be that way, because gravity, the force of gravity, decreases with the inverse square of the distance between those two objects. So as you're getting closer, that force of gravity is going to be stronger, and that's going to cause it to curve around and make that elliptical shape. All right. Kepler's second law. Kepler's second law relates the speed and the distance. It states that a planet's move in its orbit, it sweeps out an equal amount of area in an equal amount of time. So if you look at these 2 diagrams, this is 1 month of time. And so if you took the area of that shape, and this is 1 month of time, and you took the area of that shape, then they would be equal to each other. And the same here. So at any space in time, the area of that path is going to be the same. That's Kepler's second law. All right, and Newton explains it. So Kepler's second law follows the fact that the force of gravity on a planet pulls directly towards the sun. And so it exerts 0 torque on the sun. So the sun is not moving necessarily. So it's the planet moving around the sun. So there's a pull. The planet pulls directly towards the sun. So there's 0 torque on the sun. So the sun is like the axis. Okay. and then the planet is moving around the sun. Since there's no torque acting on the planet, then angular momentum has to be conserved, which is why any area in over the same space of time, any area has to be the same area because your angular momentum gets conserved. That area that gets swept out in that particular amount of time has to be the same. He was also able to show that the conservation of angular momentum is equivalent to Kepler's equal area law. So Newton went back and showed that Kepler's second law followed with Newton's universal law of gravitation, that the planet pulls on the sun. That means there's no torque on the sun about the sun itself because the sun is acting like the axis and its planet's revolving around it. So any space in time, any area that's swept out in that particular space of time is going to be equal. And that's the same as like saying its angular momentum is conserved. Oops, I forgot to erase that. There we go. All right, Kepler's third law relates the distance of the planet from the sun to its orbital period. And the orbital period is the time it takes for the planet to make one complete orbit. That's its period. So Kepler found that in a simple linear or quadratic relationship between the period and distance didn't fit his experimental data. So it's not just a direct relationship or a linear relationship or even a quadratic relationship. What he was able to show was that the period depends on a 3/2 power of the distance. Okay, so I'm going to show you the formula for that in just a second. So in a quadratic, remember a quadratic relationship would show that it was something to the second power. A linear relationship would show that it is something to the first power, but it's actually somewhere. It's not a whole number. It's the 3/2 power that it's related to. So let's look at the equation for that. So here's the actual equation for Kepler's third law. The period, capital T, of a planet increases as its distance from the sun, r, is raised to 3/2 power. So here's the formula. T equals the distance from the sun raised to the 3/2 power. And of course, there's a constant that you're going to multiply that by to make it a relationship. Newton was able to find out what that constant was. He was able to show that Kepler's third law also followed the law of gravitation and was able to derive the mathematical expression for that constant in Kepler's third law. So this is the actual equation to find the period of a planet's orbit. It's 2 pi over the square root of universal law of gravitation times the mass of the sun. And then you have times the radius of the sun raised to the 3/2 power. Okay. All right, so these graphs kind of show that. These are all plots of Kepler's third law. The center curve, this one right here, along with the two other possible mathematical relationships between the period of revolution and the mean radius from the sun. So this would be if it was a quadratic relationship. Okay, because it's x to the square power. This would be if it was a linear relationship, because it's a straight line. What we actually see is it's something in between those two. So it's the period is related to the radius to the 3/2 power, not squared, not 1, not first. Okay, so this would be the actual data. And so Kepler could see that this doesn't work. The actual data doesn't match with it being a quadratic relationship or being a linear relationship. And then Newton went on to find out what that constant that you're going to multiply that by was and how to find it. Okay. Newton's results, the period of the planet depends on the mass of the sun, not the mass of the planet. So in general, the period of an orbiting planet or moon depends on the mass of being orbited. So it doesn't depend on its mass, it depends on what it's orbiting. Okay, so that's why for the period of a planet, it's equal to the mass of the radius of the sun. Okay. Kepler's law can be applied to the moon or to just any satellite orbiting a planet. And you can find the period of that satellite orbiting the Earth when we replace the mass of the sun with the mass of the Earth. So this is the same formula that Newton came up with, but instead of saying mass of the sun, which would be what it was for us as Earth orbiting the sun, this would be for a satellite that's orbiting the Earth. So you have to include the mass of the Earth because that's what it's orbiting. It's orbiting the Earth. Okay. All right. So just kind of note that distinction. And when you're doing problems, you're going to need to make sure you know what is this thing orbiting? Is it orbiting Earth? Is it orbiting Pluto? Is it orbiting Jupiter? Is it orbiting the sun? Because that makes a difference as to what you put into this formula for the period. Okay. All right. So some applications of this information, geosynchronous satellites are probably the best application for this. The geosynchronous satellite is one that orbits the Earth with a period equal to 1 day. From Earth, such satellites appear to be in the same location all the time, but they're really not. They're moving around, but their period is 1 day. Geosynchronous satellites are useful for communication and weather forecasting. These are all communication satellites, that kind of thing. Kepler's third law, from that, we know that a satellite has a period of 1 day only if its orbital radius has a particular value. So in order for it to have that orbit or have that period of 1 day, you have to put it at a certain height or certain radius above the Earth. And so the next example looks at how we calculate what that altitude or that height is supposed to be. Okay. So we want the period to be 1 day, which is 8.6 times 10 to the 4 seconds. We have our radius of the Earth. We know our mass of the Earth. So we're just going to plug all that information into the Kepler's third law, and we're going to find little r. Little r would be the radius. Now notice so little r is the total radius of as far as how far above the Earth it's going to be, including the radius of the Earth. So would be from the center of the Earth to wherever it is here. Okay, so this is our capital E. That's the radius of the Earth. And what we want to know is what's this height right here. Okay, so that's why this last step, we have to subtract our little r from the radius of the Earth to find out the height above the Earth. That's its altitude. So don't forget to do that in your problems. So this r here that they're referring to is going to be this whole distance from the center of the Earth to the satellite itself. And to find out how high above the Earth's surface that is, we have to then subtract out the radius of the Earth. Okay, so all geosynchronous satellites orbit at an altitude of 22,000 miles, if we convert the meters to miles, 22,000 miles above the Earth. Okay, now not all spacecraft are put in geosynchronous orbits. Our GPS system, our Global Positioning System satellites, do not go at 22,000 miles. They go at 12,500 miles above the Earth. And so this is a system of 24 satellites, and probably maybe more now, I don't know. This is when this book was written, that make it possible, of course, to know your location and where you are going or how to get there. And we know it with very good accuracy. And that's because they're at a lower altitude, and there's 24 of them all kind of working together. But that is not what we call a geosynchronous orbit. Okay, that is it for 9.4. This is the last section in chapter 9.